In this lecture, we are going to talk about alcohols, which is one of the most important functional groups in organic chemistry. This will include its structures, properties, and reactivities, but in the first clip, we will just mention about structures and properties. So alcohol is the compound at which the main functional group is the hydroxy group or this OH group. You might have seen alcohols in the form of ethanol, methanol, or isopropanol. And when we do the nomenclature of alcohols, we are going to use the suffix, which is the phrase that we put at the end of the name in order to specify the main functional group of the molecule. And in this case, we are going to use the suffix of ol, ol, at the end. For example, this molecule, if you imagine this molecule without an hydroxyl group, so this would be an ethane. But since we have the hydroxyl group here, then we need to specify it by cutting the E out and put the suffix, which is ol. So at the end it becomes ethanol as an IUPAC name. For the second molecule here, without the hydroxy group, it would be methane. And if you cut the E out to specify that it is an alcohol and put the OL, it becomes a methanol. For last compound, without the alcohol, it would be a propane. However, in this case, the alcohol could connect to the first or second position of the carbon. So in this case, if you count the number in the chain, the alcohol, the hydroxyl group, is connected at the second position. So we need to specify number 2 here, and then it becomes propane 2-ol like this as a name. And you can see that in nature there are several compounds that contain alcohol as well. For example, this menthol, you can see that the name also have ol as a suffix, reflecting that this compound should have the hydroxyl group in the molecule as well. If you look at the structure of alcohol, you can see that this oxygen is sp3 hybridized, which is tetrahedral in geometry. This is the same as the oxygen of water. And another common thing is that both of them has an available lone pairs, 2 sets of them in the sp3 orbitals. And you can see that this is reflected in the red region here, which means that it has high electron density. And from our first lecture, we would predict that the oxygen here might be able to act as a nucleophile. And if we have an electrophile, it could get attacked by these lone pairs. Okay, so this is the first mode of action of alcohol, by the oxygen behave as a nucleophile attacking some sort of electrophile. Another mode is that if you look at the electronegativities of oxygen compared to carbon and hydrogen, you can see that oxygen has much higher En than the other 2 atoms. Therefore, it will pull the electron away from these 2 atoms next to it, which reflects in the deep blue region here and here. And with this lack of electron density, so it would have slight positive charge, and therefore both of them can act as electrophile. If you have a nucleophile, it might be able to abstract the proton here, or it might be able to attack the carbon here, depending on the reactions. So these are 3 important modes of actions that I would like you to understand from the structure of the alcohol, and we will come back to this later in lecture 2 to 3, lecture 2, 3, and 4. Alcohols can be classified as either primary alcohol, where the carbon that connects to the OH group connects to only one other carbon, okay, or it could be classified as secondary alcohols where the carbon that connects to the hydroxyl group connects to two other carbons. The tertiary alcohols is the one at which the carbon connected to hydroxyl group connects to three other carbons. And last type of alcohols is phenols, where the hydroxyl group is connected to the aromatic ring here. If you look at this example, for the first molecule, the carbon that connects to hydroxyl group connects to three other carbons. Therefore, this is a tertiary alcohol. For the next molecule, the carbon that connects to hydroxyl group connects to only one carbon. Therefore, this is a primary alcohol. The next molecule, cholesterol. The carbon that connects to hydroxyl group connects to two other carbons. Therefore, this cholesterol is a secondary alcohol. And lastly, 3-methylphenol. Obviously, this hydroxyl group connects to the aromatic ring. Therefore, this is classified as a phenol. Next, we are going to talk about the physical properties of alcohols, including its boiling point, melting point, and solubility in water. And in order to understand and compare these properties, you need to understand the very important concept, which is the intermolecular forces, which is a force that bind molecules to each other. The intermolecular forces can be divided into three types. London dispersion forces, where you have, for example, two molecules, although if it doesn't have any polarity, maybe it's a neutral molecule, but at some point the electron might migrate and make one side like partial positive charge and the other one partial negative charge. This will induce the electron distribution in another molecule, and this creates the interaction, intermolecular interaction between these two molecules, holding these two together. This interaction is increased when the size of molecule increase or when the molecular weight increase, since you have more electron to work with. The next type of interaction is the dipole-dipole interaction. This occurs when your molecule has a permanent dipole, meaning your molecule is polar, and this could happen when one of the atoms in your molecule has high En, and this will pull away electron from the other part and makes this positive and this negative. Therefore, you can have two molecules or more that so the positive charge of one molecule will interact with the negative charge of the other molecule, and this creates the dipole-dipole interaction, which hold these two molecules together. The last type of interaction is hydrogen bonding. So if your molecule has an atom that has very high electronegativity, like fluorine, oxygen, or nitrogen, and then this attached to hydrogen, this high electronegative atom will pull electron away from hydrogen, and this creates a strong positive charge on the hydrogen and strong negative charge on the FON. So another molecule with FON can then use its negative charge to bind with the positive charge proton here to create the hydrogen bonding. So the first thing we are going to compare is the boiling point. If we imagine that in order for molecules to boil, we need to separate the molecule, one of the molecule apart from others, and therefore we need to break these intermolecular forces. Therefore, if you have higher intermolecular forces, then the boiling point would increase because you need more energy to break these intermolecular forces. So if you compare between alcohols, ether, and alkane with the similar molecular weight, for example, ethanol with molecular weight of 46, dimethyl ether of molecular weight of 46, and propane molecular weight of 44, therefore the London dispersion forces should be very similar between these three series. However, you can see that there is a large increase from alkane. The propane has boiling point of minus 42. Ether has boiling point of minus 25, and ethanol has boiling point of 78, which is much higher. And this is due to the second interaction which is the dipole. We can see that propane is quite a nonpolar molecule with the dipole moment of only 0.08. However, with the oxygen in the molecule, it creates the dipole moment and with 1.3, and therefore the dipole of dimethyl ether is higher than propane, and therefore the intermolecular force higher, and it has much higher boiling point. And for ethanol, it also has similar dipole moment, but in this case it has much higher boiling point, and this is due to the extra hydrogen bonding, because for alcohols you have the high electronegativity atom connected to hydrogen, and this creates the hydrogen bonding between each molecule. As you can see, the oxygen creates negative charge and the proton makes positive charge, which interacts with the negative charge of the other oxygen. Okay, and this creates kind of like a network and requires more energy to pull away one molecule as required for boiling. Okay, for this example, you need to rank the compound from the lowest to highest boiling point. Okay, one thing that is much different from the others is this molecule. It is just a simple alkane, but it consists of very long chain, and although it doesn't have any dipole interaction and the hydrogen bonding, but the London dispersion force is very high, and this wins out, and it has very high boiling point here. So this should be number 1. If you compare between the rest of the series, you would imagine that the alcohol would have highest boiling point, right? Because it can form hydrogen bonding, and the rest of these has similar molecular weight. So these two should be number 2nd or 3rd. However, because the right hand side molecule here is larger, and therefore it has higher London dispersion force than, so both of them has dipole interaction, it has hydrogen bonding, but on the right hand side molecule has much higher London forces. So this right hand side molecule is the 2nd most highest boiling point, and therefore the left hand side molecule is the 3rd highest in boiling point. Okay, If you compare between these three molecules, you would see that they have similar molecular weight. Therefore, we will compare only the hydrogen bonding and dipole-dipole interaction. For ether, you have the dipole-dipole interaction, but you don't have the hydrogen bonding. For alkane, you don't have a dipole-dipole interaction and you don't have hydrogen bonding neither. So the ether is the fourth place and the alkane here is the last place. Another important property is the solubility in water. For the boiling point, we look at the interaction between the molecule itself, right? But for the solubility in water, we are going to look at the interaction between the molecules and water. If it has high interaction, that means it is like quite favorable to dissolve in water. Therefore, your molecule should be able to form hydrogen bonding with the water molecule, and your molecule should be quite polar in order to be soluble in water, because water is a polar molecule. Okay, so if you look at the trend of alcohol, for methanol or methyl alcohol, you have CH3 and OH. You can see that this hydroxyl part is the part that can form hydrogen bonding with water, because this negative part can form hydrogen bonding with the positive charge hydrogen of water, and this positive charge hydrogen can form hydrogen bonding with the negative charge of the oxygen of water. Okay, so we call this hydroxyl group as a hydrophilic region or water loving region. And the alkyl chain, it cannot form any hydrogen bonding and it doesn't have dipole, so this doesn't like to dissolve in water, and we call it hydrophobic region. In order for alcohols to be soluble in water, you need to have low hydrophobic region, such as methanol. It has only CH3 groups, therefore it is miscible with water. With an extra carbon in ethyl group, it is still miscible. For propyl, it's still miscible. However, if you keep increasing the solubility, if you keep increasing the area of hydrophobic region, for example, pentyl alcohol, now you can see that the hydrophilic region is only hydroxyl group here, but the hydrophobic region is this long chain here, and therefore this starts to be less miscible in water and only 2.7% solubility here. If you even keep increasing to hexyl, this is even lower. But if you have more than one alcohols, more than one hydroxyl group, like hexane 1,6-diol, you can see that it has two hydrophilic regions and makes the molecule more soluble in water, and now it is miscible with water because it has two hydrogen bonding groups. For this example, if you need to rank the compound from the one with lowest to highest solubility in water, you can see definitely this compound doesn't have any hydrophilic region at all. It's just an alkane. Therefore, this one is not soluble in water, definitely. Okay, so this is the worst soluble in water. And this long chain alkane is normally used as the organic solvent or grease that like separate from water. And for the rest of the molecule, you can see that all of them contains alcohols. Both all of them are alcohols that contain hydroxyl group. This molecule has 2 hydroxyl group. This one has only 1 and this one has only 1. Therefore, if you compare between this has 4 carbon as the hydrophobic region, but this has 1, 2, 3, 4, 5, 6, 7, 8, 9 carbon as the hydrophobic region. Therefore, this molecule is less soluble in water compared to the left hand side. And if you compare between the this molecule and the bottom one, both of them has 4 carbons, but the bottom one has 2 hydroxyl groups. Therefore, it should be more soluble in water compared to the top one. Okay, so this is the answer for this question. The next thing I would like to mention is the acidity, which is one of the chemical properties of alcohols. Before we begin, we need to understand what is acidity. Okay, so acidity is the ability for the molecules to dissociate and give out proton. Okay, this proton is the reason that molecule is acidic. If your molecule can dissociate more towards the right hand side, then your molecule is more acidic. And we have the number that can use to measure acidity as a Ka. If you can remember in Chem, it is the equilibrium constant of the dissociation of acid. It is equal to concentration of products divided by concentration of starting material. And you can see if you have higher Ka, you have more concentration of proton, and therefore your acidity increase. But when we normally report Ka, we will report in the form of pKa, okay? So which is the minus log Ka. Therefore, the lower the pKa, the higher acidity. So if you look at water, for example, it has pKa of 15.7, which we know that water is a neutral molecule, right? For acetic acid or vinegar, we know that it is a weak acid and it has pKa of 4.8, so it has like quite acidic. But for hydrochloric acid, this is a very strong acid, and we know that it is fully dissociated, right? So therefore this is a strong acid. So if you look at the values of alcohols, you can see that all of them has pKa of around 15 to the lowest one is phenol, which is 10. So we would imagine that alcohol is either neutral like water, or in some cases there might be a very weak acid, weaker than acetic acid, right? Because acetic acid is already a weak acid, but it has pKa of 4.8. So if you compare within the alcohol series, you can see that the methanol itself has very similar pKa to the water. And for the trend, if you have chlorine groups, which is electron withdrawing groups, it makes the alcohol more acidic, and I will mention about that later on. And if you have larger alkyl groups, it becomes less acidic. This is due to the decreased solvation of the alkoxide ion. Alkoxide ion is the ion that is generated after the proton dissociate, okay? So if you have larger groups, alkyl groups, the solvation of this alkoxide is less favorable. Lastly, for phenol, this is very important because phenol is much more acidic than alcohol, is 100 million times more acidic than cyclohexanol, and we will mention about this later why it is. For the first effect, if you compare between ethanol and 2-chloroethanol, you can see that if we draw out the equilibrium, the ethanol might dissociate into the alkoxide and proton, same as the 2-chloroethanol, which dissociate into the alkoxide and the proton. So we will determine whether which one is more acidic by how much the equilibrium lies towards the right hand side to get more proton, right? And from this, because 2-chloroethanol has a chlorine group with very high electronegativity, therefore it pulls away electrons from this negative charge and stabilizes it. Therefore, this lower conjugate base is more stable than the top one. Therefore, the equilibrium lies toward the right hand side more. Therefore, 2-chloroethanol is more acidic because the chlorine has high En. It stabilizes the negative charge, makes the conjugate base more stable, and shifts the equilibrium towards the right hand side to get more proton. Okay. The next properties of phenol is that the conjugate base that you form is the phenoxide with the oxygen minus next to aromatic ring, and this is very stabilized because the negative charge now can delocalize into the aromatic ring. So you can see this arrow representation. It delocalizes into this carbon, to this carbon, and to this carbon. So overall, your phenoxide ion, instead of having negative charge localized on the oxygen itself, now it's delocalized into the oxygen and three other carbons. And with this charge distribution makes the molecule less reactive, or in the other hand more stable. Therefore, the equilibrium will shift towards the right hand side more and you get more proton. That's why phenol is more acidic than alcohols due to the stability of the conjugate base. In the last example here, you are asked to rank the compound from one with lowest to highest acidity. You can see that these two molecules are phenol. Therefore, this must be more acidic than alcohols or alkene. And this phenol has chlorine with electron withdrawing group. Therefore, this will stabilize the negative charge even further. And therefore, this is the most acidic compound. And this is second most acidic compound. If you compare between these two alcohols, you can see that the fluorine is also electron withdrawing group and stabilize the negative charge when it dissociates. So this is the third most acidic, and this is the least acidic of all the alcohol series. And for the alkane, you don't have any acidic proton at all in the molecule, right? You cannot dissociate and form carbon minus because this is not stable at all. So this is the least acidic compound in this series.